Time now on Going Bush to turn up the intellectual heat, Andrew.
Yes,
and that's
Nick.
why I've brought you here to Warra. This is in fact a research station out in the forest.
Nick, it's State Forest which has been set aside to conduct experiments. Look, that's not a van, it's a science lab in the forest. Today, we're looking at carbon. Carbon accounting has become something of a buzz phrase since the whole climate change debate got rolling, and this Melbourne University PhD study is aiming to measure the surprisingly large amount of carbon dioxide and other greenhouse gases being produced by forest soils.
The soils are living, basically. If you were to strip away the minerals, there'd still be most of the soil there, most of the bacteria, the fungi, the invertebrates that are living in the soil. There's a massive community down below the ground, all chewing on the roots, the litter that falls to the soil. They're basically cycling that through, and they're respiring all the time they're doing that.
The 9-month study consists of a delicate web of tubes, traps and analysing equipment, and for the first time is giving us a more complete picture of the forest's carbon exchange cycle. And so, Tim, this is part of the experiment that measures the breath coming up from the soil.
That's right, Nick. The lids of these chambers will close up. When they close, the machine sucks a sample of the air up into the van where they measure the gases that are released from the soil.
It's not just the soil that is breathing, it's also the logs that are lying on the forest floor. I'm joined by Dr. Simon Groves, who describes himself as a deadwoodologist. Mate, what are we looking at here?
We're looking at rotting logs and their role in the carbon cycle on the forest floor here.
How quick for a log to rot?
Well, that was a question we set ourselves. It's a difficult one to answer because in this sort of forest, we don't know how long these logs have been on the ground in the first place, and so it's a real detective story to try and come up with those numbers.
So there's carbon being stored in those logs, but there's also carbon being released?
Yeah, that's right. They store a huge amount of carbon, but in terms of releasing it, it's all the creatures that are living in there that are breathing away, decomposing the log, and they play a very prominent part in the carbon story for the forests here.
It's a dirty job. Cool climate eucalypt forests have between 100 to 500 tonnes of dead wood per hectare, and determining how quickly that wood is decaying is key to accurately accounting for the amount of carbon being released.
We use chainsaws to chop up about 200 or 300 logs to look at the rots inside them to start with, and then we have to take samples of all those rots and take them back to the lab to work out the carbon content. But then in terms of figuring out how long these logs have been on the ground, we need to use a range of approaches. This log here, for instance, has got myrtle trees growing out of it, and you can take a core to those myrtle trees. You can take a core sample, and use the tree rings to work out how old the myrtle tree is, and from that gives you a minimum age for the time since the log arrived on the ground.
The upshot is that decomposition times are longer than previously thought, a decent-sized log taking a good 200 years to finally break down.
To start with, we didn't think we knew very much because we didn't. And if we had just taken results from other people's studies in the tropics or in the Northern Hemisphere, we would have been way out. So it's very appropriate that we do this research locally, and it's telling us a different story from other parts of the world.
So in the carbon sort of accounting, Hardy, we've got not only the ground respiring and the logs rotting away, we've also got water.
Nick, to do a big picture carbon cycle, we've got to take into account all manner of things, including how much carbon is running away in the rivers. Research Officer Ian Riley has spent plenty of time looking at just that question. The process of sampling and analysing creek water running off a particular catchment area has provided a first look at the part played by water in the carbon cycle.
And so my sample is drinking water, not much colour. Yours is from the creek.
Yeah, and we've used the colour as a means to give us an indication as to how much carbon is contained in the water.
So colour, in this case, is carbon?
Yes.
And you might be surprised to learn just how much carbon is carried away in that light shaded yellow.
In terms of over a whole year, Warra Creek behind us is exporting 100 tonnes approximately of carbon out per year out of this catchment area, and the forest itself would be absorbing about 1,000 tonnes from the atmosphere into itself per year for a catchment of this size.
It all adds up to a clearer, more accurate assessment of the carbon impacts of our forests and the ability to use that knowledge to better manage them for future challenges.
We can understand, for example, how the forests are responding to particular weather events like droughts, wet years, dry years. What's the difference between a wet year and a dry year, and how much the forests are absorbing carbon versus how much they're releasing? What happens when there's an insect outbreak, defoliating insects? How much does the forest lose carbon during those events? And by knowing those specific events, we can then look into the future and look elsewhere to see, well, how are these events going to change in the future with, say, climate change or areas that are more prone to insect attack? What's going to be the consequence on the amount that forest can store carbon?
So to sum it up, even if it just looks like dirt, forest soils are alive and definitely breathing. Rotting logs add to the carbon production side of the ledger, but more slowly than expected, and water exports a fair whack of forest carbon to elsewhere in the ecosystem, and there's no doubt that knowing all this will become more and more important to the